So according to de Broglie's hypothesis, particles may exhibit wave properties. And from the earlier works of Einstein and Max Planck and Compton, we know that light, that is electromagnetic wave, also exhibit particle properties. And later in 1925, de Broglie's hypothesis was that not only light exhibit particle properties, but particles may also exhibit wave properties. So matter in general have a dual nature. Matter have both wave properties as well as particle properties. This de Broglie's hypothesis was confirmed by Davison-Germer experiment in 1927. And what did Davison and Germer do? They performed diffraction of electrons from single crystal of nickel. The diffraction pattern could be explained if the electrons have a wavelength given by the de Broglie wavelength, that is lambda equal to h by p. These experiments show that electrons behave like waves because only waves can interfere and produce the interference pattern. And only waves can produce diffraction pattern. Particles cannot produce diffraction pattern. In 1928, G.P. Thomson carried out electron diffraction experiments by passing electrons through thin polycrystalline metal targets. And later on, various other experiments were performed with not only electrons, but also with protons, neutrons, and even atoms. And all of them showed that these protons, neutrons, atoms, electrons, they also exhibit wave-like properties. And the wavelength is related to the momentum of these particles through the de Broglie relation. And what is the de Broglie relation? The de Broglie relation says that the wavelength is equal to h by p. What is h and what is p? Can someone tell me? H is the
Planck's constant.
Planck's constant, and p is the
Momentum.
P is the momentum. H is the Planck's constant. From this relation, we can also write P as h bar k. P as h bar k. What is h bar and what is k? What is h bar? Have you come across this
Reduce Planck's constant.
Reduce Planck's constant. Reduce Planck's constant. And what is k?
Wave vector.
K is the magnitude of the wave vector. Okay. So from this relation lambda equal to h by p, from this relation lambda equal to h by p, we can see that. From this relation, we can see that P is equal to h times h by lambda. So from lambda equal to h by p, we can see that p equal to h by lambda. To this, you divide and multiply by twice pi. Divide and multiply by twice pi, or in other words, you divide h by 2 pi and then you divide 2 pi by lambda. So this can be written as let me erase this, clear my drawings. Let me repeat this. P equals h by lambda. And this can be written as h by twice pi, then twice pi by lambda. This twice pi and this twice pi, they will cancel out. Let me try to erase it. This is not h by twice pi, and then it should be lambda by twice pi. It should be lambda by twice pi. Oh, so this twice pi and this twice pi, they will cancel out, and we are left with h by lambda. And this can be written as, what is h by twice pi? H by twice pi is nothing but h bar. This is h bar. H by twice pi is the reduced Planck constant, h bar. And this can be written as lambda by twice pi. This can be written as 1 by k. Or this can be written as 1 by k. 1 by k. So this implies p equal to h bar k. I got 1 by kj. I can bring k to the numerator, and this becomes h bar k. So we have p equal to h bar k. And what is k? K is twice pi by lambda. What is k? K is twice pi divided by lambda. K is twice pi by lambda. Therefore, lambda, this lambda by twice pi, this is nothing but 1 by k never. P equal to h by lambda. Say that you divide both numerator and denominator by twice pi. Then in the numerator you get h bar. In the denominator you get 1 by k. Then you bring k to the numerator, and we have h bar k. So this is how we obtain this relation p equal to h bar k. So the p equal to h bar k. Here p is the momentum, k is the magnitude of the wave vector. And this relation is nothing but the de Broglie relation written in a different form. So p equal to h bar k is nothing but the de Broglie relation written in a different form. So from now onwards, you should remember that p is equal to h bar k, where h is h by twice pi. It is the reduced Planck constant, and k is the magnitude of the wave vector. So this is the relation between p and k in one dimension. We can extend these relations to three dimension, and we obtain p vector equal to h bar k vector. P vector equal to h bar k vector. So in three dimensions, it has three components. And what are the three components? The three components are this: px equal to h bar kx. The other component is py equal to h bar ky, and similarly pz equal to h bar kz. So this relation, this is a vector relation in three dimensions. It has three components: px equal to h bar kx, py equal to h bar ky, pz equal to h bar kz. And what is k here? K denotes the wave vector. Now in three dimensions, what is the relation? What is the relation between k vector and lambda? In one dimension, in one dimension, k equal to twice pi by lambda. But in three dimensions, what is the relation between k and lambda? In three dimensions, what is the relation between k vector and lambda?
K vector is equal to K vector is twice pi by lambda kemarin. Inversely, interpretation now inversely proportional ordinary.
In three dimension, k vector equal to twice pi by lambda. See, Abra, left hand side is a vector, right hand side is a scalar. So we need to do something with it.
Unit vector mahapan.
Unit vector mahapani. Adusu yadri. What should we do? This left hand side, it should be a scalar. It should be the modulus. It should be the modulus of k vector. The left hand side, it should be a modulus of k vector. Unit vector this is easier. The the modulus of the k vector is equal to twice pi by lambda. This is the relation between k vector and lambda in 3 dimensions. So here this k, you can think of this k as the magnitude of the wave vector. This k is nothing but the magnitude of the wave vector. As established by Einstein's explanation of the photoelectric effect, the energy E of the particle is related to the frequency through the relation E equals h bar omega. E equals h bar omega. Okay. E equals h bar omega. From Einstein's photoelectric effect, what had we obtained from the photoelectric effect? We had obtained that E equal to h nu never. We had obtained E equal to h nu. Sigi relation data, what do? Simply we divide and multiply by twice pi. So h divided by twice pi times twice pi times nu. What is nu? Nu is the frequency. So h by twice pi. What is h by twice pi? H by twice pi is h bar. And what is twice pi times the frequency? Twice pi times the frequency is the angular frequency omega. So E equal to h nu haibasiga, E equal to h bar omega haibasiga sapmanaiko. So there is no difference between E equal to h nu and E equal to h bar omega. Here omega is twice pi times the frequency. So omega is the angular frequency, nu is the simple frequency. So from E equal to h nu, we have obtained E equal to h bar omega by simply dividing and multiplying by twice pi. P equal to h by lambda, simply by dividing and multiplying by twice pi, we have obtained this relation. P equal to h bar k and E equal to h bar omega, simply by dividing and multiplying by twice pi. So E equals h bar omega comes from E equals h nu. What is h? What is nu? H is the Planck's constant. Nu is the frequency of the radiation. Okay, let me clear all my drawings. Next up. Now, let us obtain an equation whose solution describes the behavior of particles, like the electron and the proton. The corresponding solutions should describe the corpuscular and wave-like behavior of the particle and should be consistent with the uncertainty principle. Thus, we assume that the particle is describable by a wave function, and that wave function is represented by capital psi, and this capital psi is a function of position and time. So what are we going to do? We're going to obtain an equation whose solution describes the behavior of particles, like electrons and protons. And since we already know that electrons and protons have wave characters, they can be represented by a wave function psi. And this psi is a function of position and time. And this equation, what we are going to obtain, this equation is called the Schrodinger equation. Here we have written the term, this term is explicitly obtained. We are not going to derive. We are not going to derive the Schrodinger equation. We are simply trying to obtain the Schrodinger equation from some simple arguments. This is because the Schrodinger equation cannot be derived. Schrodinger equation is derived to via deva. Equation simple case that obtain to VDI, but it cannot be derived. Say similarly, can you derive the Newton's law of motion? F equal to ma. F equal to ma. However, Newton's second law of motion is derived to via bro. Have you come across the derivation of the Newton's second law of motion, F equal to ma? Because these are laws which cannot be derived. Because the predictions which we obtain from these laws and equations, these predictions have been verified by experiments. Therefore, we assume that these equations and these laws, they are correct. So let us obtain the Schrodinger equation. Clear all the drawings. The particle is describable by a wave function. So this is the quantum mechanics which was put forward by Schrodinger. So Schrodinger na mana puthomba mana hogomba quantum mechanics no wave mechanics ko. Similarly, atopa matrix mechanics Heisenberg matrix mechanics and this wave mechanics and this matrix mechanics, they were proved to be equivalent by Dirac. Dirac to aduna sayida quantum mechanics the Schrodinger, he put forward the wave mechanics, and then Heisenberg he put forward the matrix mechanics, and then in 1927-28 Dirac showed that this wave mechanics and matrix mechanics, they are the one and the same thing. So in this course, we are going to study the wave mechanics put forward by Schrodinger. Schrodinger na puthomba wave mechanics to them. Okay, so let us try to understand what Schrodinger equation is. For that, let us consider the non-relativistic. So let us consider the non-relativistic motion of a free particle of mass small m moving along the x-axis with a well-defined momentum p. Here p vector equal to p x hat, where x hat is the unit vector along the x-axis, and the particle has a corresponding energy capital E. It is a free particle. And what is the meaning of a free particle? Free particle, can someone tell me the meaning of a free particle? Say the free particles data. What does the word free actually mean?
Free from external forces.
Yes, that is right. Free from external forces. There is no external force acting on the particle. So free means there is no external force acting on the particle. So if there is no force acting on the particle, which quantity remains constant? Particle the external force amata ek tawdragadi. Particle the external force amata ek tawdragadi, which quantity remains constant? The potential energy of the particle remains constant. When there is no external force acting on the particle, the potential energy of the particle remains constant. So for a free particle, the potential energy has a constant value, and that constant value can be easily taken to be zero. That constant value can be easily taken to be zero for simplicity. Next question is why? Zero lo where is it? Constant potential and that constant potential can be taken to be zero for simplicity. Constant potential and energy when I say potential, I mean potential energy nika. In this course on quantum mechanics, whenever we say the word potential, we always mean potential energy. So a free particle has a constant potential energy, and this constant potential energy can be taken to be zero. Potential energy is a constant, or you can very easily take it to be zero. The way I okay, let me give you one hint. So let me give you one hint. Let me share the whiteboard. This is the whiteboard. Wow. Okay. I say the for simplicity, let us consider this. I have an object of mass m. Spherical object at a distance r from this object. I have another object of mass small m. What is the potential energy of the system? What is the gravitational potential energy of the system? The gravitational potential energy of the system is given by mass m, capital M and small m separated by a distance small r. What is the potential energy of the system? The potential energy of this system is G m capital M by R. Not wrong. G small m capital M by R, and this is actually a negative quantity because there is a force of attraction between these two. This G m by R. Sigi potential energy G. When will this potential energy become zero? At what value of R will this potential energy become zero? At what value of R will this potential energy become zero? I know this potential energy will tend to zero when R tends to infinity. Not wrong. When the denominator tends to infinity, this potential energy tends to zero, because when you divide any finite quantity by infinity, that fraction becomes zero. Not wrong. Any finite quantity divided by infinity is zero. So this potential energy, it tends to zero when R tends to infinity. Then let me give you another example. This capital M, let me draw it a little larger. Suppose this is the Earth. This is the Earth with mass capital M, and I have an object on the surface, near the surface of the Earth at a distance h, small h. So this is the Earth with mass capital M, and I have an object with mass small m at a height h from the surface of the Earth. For such cases, we also learned that the potential energy is given by mgh. mgh. What is m? M is the mass of the object. What is g? What is small g?
Acceleration due to gravity.
Acceleration due to gravity. And what is h? H is the height above the surface of the Earth. So when will this potential energy become zero? At what value of h will this potential energy become zero?
Zero.
H is equal to zero. So this potential energy, this will become zero when h tends to zero. But according to this formula, which we have on the right, if the radius of the earth is given by capital R, when the object is on the surface of the earth, if we use this formula, then the potential energy is given by minus G capital M small m by the radius of the earth. Natra. If we use this formula on the right, when the object lies on the surface of the earth, the potential energy is minus G capital M small m by R. Whereas we have another formula where the potential energy is mgh. And if h is 0, this potential energy becomes 0. So according to this formula, when the object lies on the surface of the earth, the potential energy is 0. But according to this formula, when the object is on the surface of the earth, the potential energy is not 0, but it is a constant quantity which is given by G capital M small m by capital R. For an object lying on the surface of the earth, potential energy is 0 oidoribra, natraga C oidoribra. So let me call this equation number 1 and let me call this equation number 2. So out of these two equations 1 and 2, which one is correct? Which one is correct and which one is false? Correct equation na karambano, wrong equation na karambano.
Second one, sir.
Pasitang haun hairo tadre.
Ani shubai chum doy natro sir.
Animal chum doy ne. The answer is that both of them are correct.
Kasi ahan ba ise?
Ah.
Ahan ba ise kaya ni magi height to ahan bagi height ki valid obviously height yam niamba case ki duna wadi natro sir.
Mani height am niamba case ni. H is small compared to the radius of the earth. For small value of h, this is correct. But when the object lies on the surface of the earth, according to this formula, this is 0, but this is not 0, this is a constant. Yeah. So what is the takeaway message from here? The takeaway message is that the 0 of the potential energy. The potential energy is karamba reference level the count of the so the 0 reference of the potential energy is arbitrary. We can fix any constant value as the 0 reference of the potential energy. So from the second equation, the potential energy on the surface of the earth is a constant value, which is given by minus G capital M small m by capital R, and this is a constant value. And in equation number 1, we have taken the 0 reference of the potential energy to be this value. Aduna, the 0 reference of the potential energy is arbitrary. We can take any finite fixed number as the 0 reference of the potential energy. What is important is not the exact value of the potential energy. What is important is the change in potential energy when the object moves from one point to another point. The change in potential energy is never quite important or is the potential energy exact values we can fix the reference anywhere we like. So according to that reference, any finite constant values, we can take that finite constant value to be 0. As long as there is no change in potential energy. So what is the actually important part? What is the real part which is important? The actually important part is the change in potential energy. Change in potential energy, it does not depend upon the reference level. Finite quantity the potential energy at a point, if it is a constant, then it can be taken to be 0. So these are the two examples. from gravitation. You think about it, you ponder over this point for some time, and then you will realize that the zero of a potential energy is arbitrary. As long as the potential energy is fixed, we can easily take it to be zero value. So let us come back to the free particle. So here we are back. So say the free particle, as I said, the free particle has a constant value of potential energy. The free particle has a constant value of potential energy, and that constant value of potential energy is easily taken to be zero for ease in calculation. Then this free particle has a well-defined momentum. That is, the particle is moving along the x-axis, that is with a momentum small p, and the particle has a kinetic energy capital E. Assuming that p is greater than zero, what is the meaning p is greater than zero? Here p vector is equal to p times x hat. So p is greater than zero means the particle is moving in the positive x direction. So assuming that p is greater than zero, so that the particle moves in the positive x direction, we associate with this particle a wave traveling in the same direction with a fixed wave number k. We have already learned about the relation between p and k. What is the relation between p and k? P equal to h bar k. So if the particle has a fixed value of momentum, then it also has a fixed value of wave number k. Such a wave is a plane wave, and a plane wave can be written in this form: a e to the power I kx minus omega t. Say the kx ki mamang da le plus ni, omega t ki mamang da le minus ni ko. So if you come across an expression like this, a e to the power I kx minus omega t, you will learn that, or you should remember that this is a plane wave. It is a plane wave because a is a constant. If a is not a constant, then it can be any other wave, as a spherical wave or a top of wave or but since a is a constant, it is a plane wave. And this plane wave is traveling towards the right. How do we know it is traveling towards the right? Because you should always look for this sign. Kx ki mamang sign, the sign before kx is positive, whereas the sign before omega t is negative. I'm going to positive or I'm going to negative or you should always remember that the wave is traveling towards the right. So this represents a plane wave which is traveling towards the right with a wave number k and angular frequency omega. As I said, this is a wave which is traveling towards the right. And what will be the form of a wave which is traveling towards the left? Traveling towards the left, are traveling along the negative x direction? That's a wave form. What will be the form of a wave?
Minus x locked in.
Kx ki mamang da label sign duga, omega t ki mamang da label sign duga chap managatawa. So for a wave which is traveling towards the left, if it is a plane wave, then the coefficient a should be a constant. A should be e to the power I, it should be kx plus omega t. This is a wave which is traveling towards the left. So the kx ki mamang da label sign ju plus ni, omega t ki mamang da label sign ju plus ni. This is t. Sign and it is a wave traveling towards the left. Here also we can have a negative sign. This is the negative sign happen to change like this. The positive signs happen to change like this. What we should compare is the sign between kx and kx ki mamang da label sign jiga, omega t ki mamang da label sign jiga. You should compare these two signs, and if these two signs are the same, it means it is a wave traveling towards the left. You recall? And here the sign before omega t is negative and the sign before kx is positive. It means this is a wave traveling towards the right. If you want to know why why it is a wave traveling towards the right and why it is a wave traveling towards the left, then I recommend that you read the book on electrodynamics by Griffiths. Have you heard about the book written by Griffiths on electrodynamics?
Tarisha.
It is given there in that book. It is given there. Salida aniji ki science manadragadi, it is a wave traveling towards the right. Aduga salida science manadragadi, it is a wave traveling towards the left. It is given in the book by Griffiths. Adu yengo, aduga you will learn that this is a wave traveling towards the right. So since we know that matter has wave as well as particle property, this particle which is moving towards the right with a momentum p and energy E, it can be represented by a plane wave because it is a free particle. So it is a plane wave. It can be written as psi equal to a e to the power I kx minus omega t, because the plane wave is traveling towards the right. Therefore, we should represent it by a wave moving towards the right. And we already know the relation between k and p. I think we should start with this second expression and come to the first expression, because this p represents momentum of the particle, this E represents energy of the particle. So this is the plane wave representing a particle which is moving towards the right with a momentum p and energy E. And we already know the relation between k and p. What is the relation between k and p? The relation between k and p is that p equal to h bar k and E equal to h bar omega. So this p by h bar, it can be represented by k, and then E by h bar, this E divided by h bar, it can be represented by omega. So this expression and this expression, they express the one and the same thing, because k is nothing but p by h bar and omega is nothing but E by h bar. That is what we learned in the last slide, in the previous slide. Recall. That is what we learned in the previous slide. So P equal to h bar k and E equal to h bar omega. So we are simply using this relation here. So this plane wave and this plane wave, they represent the same plane wave. Here A is a constant and k is p by h bar, and the angular frequency omega equal to E by h bar. Now, if we differentiate equation 1 with respect to time, so let us differentiate this equation 1 with respect to time. With respect to time, ID, you take the partial derivative of this with respect to time. So this partial derivative, A is a constant. Aduna constant, we can take it outside. And partial derivative of e to the power I times something is first e to the power. So let me write it on a whiteboard. So let me clear all drawings first. Here, what have we obtained? We have obtained that psi xt equal to a e to the power I kx minus omega t. This was also written as a e to the power I, and this k, it was replaced by p by h bar, then omega was replaced by E by h bar. So I can take the h bar outside and place it here. So if I differentiate this psi with respect to t, del psi by partial derivative, del psi by del t, this will be, we'll take the partial derivative of this with respect to t. So anbada sila journey a e to the power I is px minus et. Then multiplied by, now you differentiate this function with respect to t. There should be an h bar here. Now you differentiate this exponent की power से you differentiate this term with respect to t, and what will you get? You get minus I e by h bar. Minus I minus I e by h bar. So this is equal to minus I times e by h bar. And what is this whole term? This whole term is nothing but psi. So this psi nika. So this is capital psi. So when you differentiate this plane wave with respect to t, we get minus I e by h bar psi. Similarly, if you differentiate this plane wave with respect to x once, what will you get? You sididum bagi fangani I px minus et divided by h bar. You will get this multiplied by. Now you differentiate this exponent with respect to x. So you, with respect to x, if you differentiate it, what will you get? I times p by h bar. So this is nothing but I times p by h bar capital psi. Now, if you differentiate this psi with respect to x again, if you differentiate this psi with respect to x again, ahanbo differentiation da we get ip by h bar, which is a constant. If you differentiate this again, you will get another factor ip by h bar again. So if you differentiate it twice with respect to x, so differentiate it twice with respect to x, what will you get? You get ip by h bar z factor z 2 times, so it will be squared times x. And what is this? What is I square? I square is minus 1. So this will be minus p squared by h bar squared psi. So del psi by del t, that is equal to minus IE by h bar psi. And what is the second derivative of psi with respect to x? It is minus p squared by h square, h bar square psi. So let me share my slide again. So this is what I was talking about. Del psi by del t is minus IE by h bar psi, and del 2 psi by del x square is minus p square by h bar square psi. This is what we have just obtained. This is differentiating psi with respect to t once, and this is differentiating psi with respect to x twice. And why do we differentiate this with respect to t once, and why do we differentiate this with respect to x 2 times? Because we already know the relation between kinetic energy and momentum for a free particle. We already know the relation between kinetic energy and momentum for a free particle, and that relation is the kinetic energy is equal to p square by twice m. For a free particle, we already know that the kinetic energy is p square divided by twice m. E comes from differentiating psi with respect to t once, and p square comes from differentiating psi with respect to x 2 times. So let us go back to our whiteboard again. So differentiating psi with respect to t once, we get this. So from this you solve for e. So from this you solve for e psi. E psi, therefore e psi will be equal to, you take minus I by h bar towards the left. So if I take minus I by h bar, it becomes plus I. So first it should be minus h bar by I times del psi by del t. So E psi equal to minus h bar by I del psi by del t, because we have this on the right hand side and this on the left hand side. So if I take this I h bar minus I h bar towards this side, then we get E psi is equal to minus h bar by I del psi by del t. When we multiply both the numerator and denominator by I, numerator to denominator to I na multiply to already the denominator becomes I square, and there is I square is minus 1 and c minus 6 cancel to, and in the numerator we have only I. So this is equal to I h bar del psi by del t. Sorry, this is not E, this is psi. I h bar del psi by del t. Correct? So E psi is equal to I h bar del psi by del t. And from this equation, if I take 1 minus 1 by h square on the left hand side, what do we get? P square psi equal to P square psi equal to minus h bar square del 2 psi by del x square. So from this relation, we have obtained P square psi equal to minus h bar square del 2 psi by del x square. See the minus h bar square now multiply to what we get P square psi, and this is equal to minus h bar square del 2 psi by del x square. So E psi is this, P square psi is this, and we already know that E equal to P square by twice m. This is the relation between the kinetic energy and potential energy, kinetic energy and momentum of a free particle. So E equal to P square by twice m. If I add psi on both sides, on both sides, what do we get? E psi is equal to P square by twice m psi. What is E psi? E psi is this. E psi is given by minus I h bar by del psi by del t. So this left hand side becomes I h bar by del psi by del t. This is equal to P square by twice m psi. And what is P square psi? P square psi is minus h bar square del 2 psi by del x square. This is P square psi. So this is minus h bar square by twice m. See twice m twice m. This is minus h bar square by twice m. The second derivative of psi with respect to x. So from this equation, we have obtained I h bar del psi by del t is equal to minus h bar square by twice m del 2 psi by del x square. So this equation is nothing but this equation is called the Schrodinger equation. So let me come back to my slide again. This is that equation. I h bar del psi by del t is equal to minus h bar square by twice m del 2 psi by del x square. This is what we have just obtained using this relation and these two expressions. This wave equation is known as the time-dependent Schrodinger equation for the motion of a free particle in one dimension. More generally, since the equation is linear, means each term, so this equation has only two terms, one term on the left and one term on the right. Each term is a linear function of psi. Since here it is first derivative of psi, so it is a linear function of psi. Here also it is a second derivative of psi, so it is also a linear function of psi. Linear habadi the psi square yaudeva. There are no terms containing psi square. There are no terms containing a multiplication of psi and its derivative. Psi derivative ki multiplication terms yaude. the second order derivative have any order derivative it is still a linear term as long as there are no psi square, psi cube terms, psi square term yaude, psi cube term yaude, and psi derivative plus psi multiplication term yaude. That means this equation is linear in psi, and it is homogeneous. Homogeneous means all terms contain psi. There are only two terms. One term on the left, it contains psi. There is another term on the right, it also contains psi. So that means the equation is homogeneous. So since an equation is linear and homogeneous, and then its solution will be a linear superposition of many possible solutions. More generally, since the equation is linear and homogeneous, it will be satisfied by a linear superposition of plane waves. This one-dimensional treatment is easily extended to 3 dimensions. In 3 dimensions, the angular frequency omega is connected with the wave number by the relation 3. This is not only for 3 dimensions, this is also true for 1 dimension. This is very simple expression. Omega equal to h bar k square by twice m. This expression comes from this equation number 4. Equation number 4, we know that E, what is E? E is h bar omega. So E is h bar omega, and what is P? P is h bar k. So P square means h bar square k square by twice m, and this is h bar omega. From the left and from the right, if I cancel 1 h bar, so the h baram chakre, so the h baram chakre, adu this the omega equal to h bar k square by twice m. So it is this expression. CG expression, it can be written in terms of the frequency and wave number in this form. We can generalize say that this is the Schrodinger equation in 1 dimension, and we can generalize this equation to 3 dimensions. To generalize the Schrodinger, the free particle Schrodinger equation to the case of this 1 dimension equation, we can generalize it to 3 dimension equations, and then we can further generalize it to the case where the particle is not free. Particles are free. So this is a particle in a field. To generalize the free particle Schrodinger equation to the case of a particle moving in a field of force, I cannot an external force acts on the particle now. Assume that the force acting on the particle is derivable from a potential. I think in this course on quantum mechanics, when we say potential, we mean potential energy. So F equal to minus gradient of potential energy. Force can always be, if the force is a conservative force, it can be written as the gradient of a potential energy. This is what you learned in your first year graduation course. This force, if this force can be written as the negative gradient of a potential energy, so that for a classical particle, the total energy E is given by the sum of its kinetic energy, P square by twice m, and its potential energy, V. Then E becomes, for a free particle, it was simply E equal to P square by twice m. But for a particle which is acted upon by an external force, the particle now possesses a potential energy which is not constant.
Sir. Other target is the apply target force. She force conservative force or the
Mane. This is a conservative force. We are considering the special case where the force is a conservative force.
Sir, Huziki sir linear equation dy by dx magi power whole square later non-linear
non-linear. Dy by dx whole square non-linear.
Order the cunning because came
order the cunning order the cunning but dy by dx whole square non-linear.
Thank you, sir.
From your theory of differential equations, theory if an equation is linear and homogeneous, Sigi equation jigi suppose psi 1 and psi 2 are two solutions of this differential equation, then a linear combination or a linear superposition of psi 1 and psi 2 will also be a solution. Siniko. Yareko. So if I repeat, if a differential equation is linear and homogeneous, aduga, since this is a second order differential equation, magi solutions, aduga partial differential equation or vanina magi solutions, mayam laigani, aduga magi general solution dudi, magi sigi solution mayam dugi linear combination organable. Yareko aduna linear and homogeneous orgadi magi general solutions, it will be a linear superposition of its many possible solutions. Aduna, if the particle moves under the influence of an external force, then the potential energy of the particle will change from one position to another. So the potential energy then becomes a function of position. It can also change with time. This is the most general case. But in this course on quantum mechanics, we are going to consider only those cases where the potential energy depends only upon position. It does not depend upon time. Adugi specific case to the specialized discuss, but for time being, we consider that the potential energy can depend upon position as well as time. So for a particle moving under the influence of a force, the total energy is given by this expression. The total energy is given by this expression. Let me add something here. Now, if I let this whole equation, if I let this whole equation act on psi act on psi e psi E psi, if you remember, E psi is I h bar del psi by del t. Let me show you my whiteboard again. E psi. Here E psi is I h bar del psi by del t. And what is P square psi? P square psi is minus h bar del psi by del 2 psi by del x square. So P square by twice m psi manaba minus h bar square by twice m del 2 psi by del x square. If I add, let me use another color here, red, maybe red. Right hand side to the P square by twice m. So the right hand side to the P square by twice m. If I add a term V, which depends upon R and T, V psi, what do? We simply add V psi here. So free particle Schrodinger equation to the particle in a field of force study extra term. For a particle moving under the influence of an external force, we simply need to add this extra term V psi. So let me come back to my slide again. Aduna, already, if we let sorry, let me annotate again. If we let equation side act what will we get? We will get here E psi E psi is I h bar del psi by del t. This is equal to P square by twice m psi. This is minus h bar square by twice m, the partial derivative of psi with respect to x twice plus V psi. V will remain as it is, V operating on psi. This is
the terms del square psi by del x square. mathematical definition at the magi physical interpretation I'm still like by the del psi by del t something wave function with respect to time happening now.
Money.
Del square psi upon del x square combine interpret know.
This is the Laplacian of psi. Laplacian and tambado. Nijamra.
Okay, Laplacian. Okay.
Laplacian of psi. This is
okay.
See, I know one dimension. The ibagi del 2 psi by del x square 1 ever. In three dimensions, this will be replaced by the Laplacian of psi. Ado 3 dimension ki case the unit 4 the lakane ever. Unit 4 the lakane aduna I know 3 dimension either 3 dimension the kono either again because unit 3 the Sarsaman and then have the unit 3 the no study to say only one dimensional cases in unit 3 and we will study the 3 dimensional cases in unit 4.
Sir. Laplacian ki magi geometrical interpretation ki wajah.
Laplacian ki geometrical interpretation ja. Ado di electrodynamics ta uchata ya roy. So kai de electrodynamics ta the Laplacian of potential is equal to 0. That is called a Laplace equation. The Laplacian of potential is equal to minus rho by epsilon naught. Rho by epsilon naught. That is called the Poisson's equation. Aduna adugi Laplacian hypothesis and how a quantity changes from position to position gradient in a gradient to be amuk divergence amuk low. In simple words, how the quantity depends upon space having the second order derivative low. Second order derivative with respect to space having magi chapchaba physical interpretation C O ni haragadi the magi solution to the aduna tragedy say for example Laplace equation say equina with the electrodynamics solve to kanda Laplace equation ki magi solution ki property ka tholakane ba magi boundary the maximum magi maximum na minimum lay be adugumba extra order property tholakane ba aduna Laplacian ki chapchaba physical meaning kai lege haragadi for the time being magi physical meaning to the when you solve the differential equation magi solution solution different solutions will have different properties. Second order derivative with respect to space. Second order derivative with respect to space. So this is the Schrodinger equation for a particle moving under the influence of a force. External force magi potential energy and that potential energy will also change from one point in space to another point in space. That is the potential energy. It can depend upon position as well as time. But for simplicity, in this course, we are going to study only those cases where the potential energy changes only with space and where the potential energy does not depend upon time. So this is the time-dependent Schrodinger equation. Time-dependent Schrodinger equation because see the left hand side the del psi by del t. We are differentiating psi with respect to time. This equation shows how this wave function psi changes with time. Psi wave function how it changes with time. So this is called the time-dependent Schrodinger equation in one dimension. This is time-dependent Schrodinger equation in one dimension. And if you want to extend this equation to 3 dimensions, we only need to make one small change. Say that here we'll make only one small change, and that change is this second order derivative with respect to x. this second order derivative with respect to x, this will be simply replaced by the Laplacian operator. So let me try to write it here. So let me write it here. In three dimension, it should reduce to square. It should be h square, then the Laplacian of the wave function psi. So this is the time-dependent Schrodinger equation in 3 dimensions. In 1 dimension, this Laplacian becomes del 2 psi by del x square in Cartesian coordinates. So in your unit 3, many of the problems can be solved by writing the Laplacian in Cartesian form. But in your unit 4, when you try to solve the hydrogen atom, okay, before coming to that, say that this Schrodinger equation, as I have said, this Schrodinger equation cannot be derived. This Schrodinger equation cannot be derived. What have we shown here? What we have shown here is that when say the mamangi, say the what we have shown here is that a plane wave which represents a free particle, it satisfies Schrodinger equation. Plane wave which represents a free particle, that plane wave satisfies Schrodinger equation. Aduga idea extend plane wave nataba. How about a particle which moves under the influence of a force? Okay, if the particle moves under the influence of a force, then let us postulate that the particle satisfies an equation of this form. Form the equation I'm satisfied to win in postulate to whenever. Chikanana Han Hogurakuno, Schrodinger Hogurakunever. Schrodinger Harakani, a free particle will satisfy an equation of this form. I would do Madikange, Schrodinger Heisenberg, not only a free particle. Any particle which is under the influence of a force, it should satisfy this equation. VR wave equation. Sigi proof like bra, sigi proof till late day. Sigi proof till late day. Proof till late day, it comes from the mind of Schrodinger. So can we derive the Schrodinger equation? The answer is no. We cannot derive the Schrodinger equation. It comes from the mind of Schrodinger. Schrodinger ki wakal lay tholopani si derived away ade. When Newton's second law derived away adaba to minor, this Schrodinger equation cannot be derived. We have to then how do we know this equation is correct? We know that this equation is correct from experience. And how do we know that? We solve this equation for psi. Psi is solved. And what does psi represent? Psi is a wave function which represents the particle. So psi is a wave function which represents the particle, and psi contains all the information about the particle. So when we solve this equation, we will get psi, and from that psi we can extract information about the particles. Say for example, its energy, its momentum, its position, angular momentum. Psi is the information we extract away to Caneva. And this information when we perform experiments and we check whether this information is correct or not, this turned out to be correct. Aduna sigi equation just chummi only from its solution and the test of its solution under different circumstances. Test or solution duna achumba experimentally obtained result to manai equation just chummi we cannot derive this equation. I repeat, we cannot derive the Schrodinger equation. Derive to where they go. Aduna let us obtain. We only obtain this equation for a free particle. Free particle amana sigumba equation am satisfied to we obtain to we have not derived this. Yaraba? Okay. Say the Laplacian in 3 dimension, this is Laplacian. So in many problems, you can express the Laplacian in Cartesian coordinates. But for a hydrogen atom, it possesses spherical symmetry. I don't know, when you want to apply the Schrodinger equation to find out the properties of the electron in a hydrogen atom, what do we take into consideration? We take into consideration that the hydrogen atom is spherically symmetric. Spherically symmetric case of vanilla. In such cases, you have to express the Laplacian operator in spherical polar coordinates. Spherical polar coordinates, the Laplacian expressed or caneva. Aduna I Laplacian operators matam chupada xyz coordinate expressed or I didn't know. Adulaite, depending on the symmetry of the situation, we have to express Laplacian. If the problem has spherical symmetry, then we express the Laplacian in spherical coordinates. If the object has cylindrical symmetry, then we express the Laplacian in cylindrical coordinates.
Sir, thank you. Sometimes the electron nucleus revolve to put case. Magi to ana magi radiation de the velocity the energy to only later.
Lay
Sigma ma'am say Sigi Schrodinger equations is Kang Bangam Dira was a point ma'am.
Yes. Magi solution solution size. Size the Kankadoni, size when a Schrodinger equation, they're going to solve the Waduni. We are going to solve the Schrodinger equation, and then we'll obtain the value of psi. We'll obtain psi in terms of position and time. Psi will be a function of position and time.
Sir, Akoina Sigi question to Miss Magi Kana was a with no.
Kana was size. So the next point I'm like three about Sig never postulate number 1 there. Sig is the state of a quantum mechanical system is described or represented by a wave function psi. The wave function contains all the information which can be known about the state of the system at any instant of time. Sig wave function psi, it contains all the information of the system. So this psi, it contains all the information about the system. Aduna in a hydrogen atom electron energy, momentum, position, angular momentum. First I need to find the wave function psi. So if I want to study the properties of a system, first I need to find the wave function representing the system, and this wave function is the psi. And this psi contains all the information about the system. And how do we extract information from psi Hebdo? That is what we are going to learn in the next few classes. Psi is the information we have to learn about information we have to come and extract over the Hebdo. The next few classes that we're going to the first important step is to calculate psi. Aduga say the Schrodinger equations in your 6th semester, either be it quantum mechanics, be it solid state physics, Schrodinger equation is not the different cases different cases you simply change V. Schrodinger equation potential energy change equations. We are going to solve this equation again and again by changing V, because different cases will have different V's. So for example, for the electron in a hydrogen atom, this V will be the potential energy of the electron in a hydrogen atom. Then for the free electron in a metal, this V will be the potential energy of the free electrons in a metal. And we know that the free electrons, the free particles have zero potential energy. In your solid state physics, when you study about your free electrons in the metal, you are going to solve this Schrodinger equation by putting V equal to 0. Solid state physics Schrodinger equation solve. When you put V equal to 0, you solve the Schrodinger equation for a free particle. Free particles approximation we assume that the electrons in a metal, that is the electrons in a conductor, are free. electrons in a conductor, when I say electrons in a conductor, I only mean the electrons in the outermost shells. The electrons in the outermost shell of the conductor are free, whereas the electrons in the inner cells are bounded. So when you want to study the properties of the free electrons, and why do we want to study the properties of the free electrons? Because the properties of a conductor, they are mainly determined by the properties of these free electrons. Aduna, when a conductor property study, we are going to solve the Schrodinger equation for a free particle. Conductor semiconductor if you want to study the properties of a semiconductor, then mainly you will study the properties of the electrons in a semiconductor. Semiconductor amagi manung dala electrons ching dudi, and adudi moina experience tauriba potential energy to karino that we put in here, and then we solve the Schrodinger equation. Aduna koina encounter tauriba different physical situations there. We can solve the Schrodinger equation for this different situations by substituting the different values of V. Different situations say Schrodinger equation solve only by replacing V by the appropriate potential energy. Class 12 solid magi band structure valence band, conduction band, energy gap that you will learn again in your solid state physics. This year you are going to learn that again in your solid state physics.
How do you?
Okay. Aduna adugi class 12 we know that a solid has valence band and forbidden energy gap and conduction band. If the forbidden energy gap is almost zero or zero, then the solid is a conductor. If the forbidden energy gap is very large, the solid is an insulator. But if the forbidden energy gap is intermediate, then it is a semiconductor. Class 12 to yaudra.
Yausha.
Adugi valence band, forbidden energy band gap, adudagi conduction band that we are going to study in your solid state physics. And how are we going to do that? We are going to solve the Schrodinger equation. We are going to solve the Schrodinger equation for the electrons in a solid by putting in an appropriate potential energy. But what is the potential energy experienced by an electron in a crystal? When I say solid, I mean a crystal. Crystal ID the latiska basiska pulaga semani have a kange. Natra. Tameko lattice is a three-dimensional arrangement of points in space. Natra. At each of these lattice points, if you add a basis, you get a crystal. So what is the potential energy experienced by an electron in a crystal? That is the billion-dollar question. Adugi, the potential energy experienced by an electron in the crystal is very complicated potential energy never. And very complicated potential energy, it is very difficult to solve Schrodinger equation. We use a simplified model. We use a simplified model, and that model is called a chronic penny model, and that you are going to learn in your solid state physics. That simplified model itself is quite complicated. The chronic penny model, this potential energy consists of whales. And potential energy, the potential energy experienced by an electron in a crystal is of this shape. We call that the chronic penny model. The chronic penny model is the base. We are going to study the properties of electrons in a crystal, and we'll find that valence band, conduction band, and forbidden energy gaps are automatically created when we solve the Schrodinger equation for such a potential energy diagram. ado sidagi hena accurate oiba potential energy ekoi sizinarga properties of solids study to vi, and that is up to you atra aduna segi chronic penny model gizu ma gizu limitation lay because
Excuse me, sir.
yes,
So we have next class too. Let's story for today.
next class at 10:30.
Yes, sir.
Okay, so you want to take rest for a while?
Yeah, we have not take offer too.
Okay, so
We can continue in the next class also, sir.
we can continue in the next class. Okay, so let me stop my recording here.
Sir.
Yeah, thank you, sir.
Let me stop my recording. For a recording stop.